GP2. Is that better? Okay. Now, you still have to check that it's functorial, right? I've given you the assignment on objects, and I've given you the assignment on arrows. But now you have to use the universal mapping property for products to see that if you compose things here, right, that this assignment will be functorial. That is, the composite of these two things that you determine will actually be the thing that's determined by the respective composites, and so on for the identity arrows. Everybody good? If you're, it's very quiet now. Okay, yeah?
If I understand this correctly,
yeah.
The idea is that F cross G maps products to products, given that F and G individually map elements in the product of...
No, there are no elements here, and there are no... Right. So this is just a map in the category, right? It's just a map. F goes from A to A prime. G goes from B to B prime. And this is a product in the category, and this is a product in the category. So I use the universal property to determine a map going from here to here. Okay? And the universal property of this thing says, this one here says, given any object and any maps into A prime and B prime, so what are my maps? Well, they're these composites. Take those two composites. That gives me maps like that. Then there exists a map right here making the two triangles commute. Well, that map that exists by the fact that this is a product, I name F cross G. So that's the specification, just in terms of the product structure. So if I know that the category has products, then I know that that product operation can be extended to a function. It can be defined for arrows as well as for objects. And that gives me that operation that I use it.
So I think you just said it, but I missed a transition from the exponential discussion to the word on the right. And so the word on the right is explaining the notation F cross line.
Yeah. So in order to define the exponential, I need to assume that I have products. And then I say the exponential has this universal mapping property. And this universal mapping property involves right there product of two arrows rather than one. So I have to define what does it mean to take a product of two arrows. And that's what I'm describing right now. Saying whenever you have products in the category, you can extend that product operation to act not only on the objects, but also act on the arrows. Take a product of two arrows. So you have, in this case, we have A going to A prime. I'm just repeating what I said. B going to B prime, out from G. I can get A cross B, A prime cross B prime, and I can get a map here that's F cross G. So that's my product operation between on the arrows. And that's, in fact, a functor. So to say that it's a functor means if I go like this, I continue, right, B double prime, G prime. If I continue like that, then I can make, again, F prime here. And then the composite of these two things will be the same as taking the individual composites and making the product of them. That's the functoriality condition, that it preserves composition. Okay? All right, good. Let's go back to the definition of the exponential now, because that's what we're really interested in. It uses this producting up operation. The exponential, this is a really, I think, important and remarkable fact that you can characterize this notion of an exponential just purely in terms of a universal mapping property and the relations to other objects in the category. It gives a universal or categorical or structural characterization of a construction that in many cases is very important and sometimes complicated. So let's look at some examples. So first of all, what about in the category of sets? Well, maybe you won't be surprised that in the category of sets there actually are exponentials, and they're exactly the function sets. The set of all functions from A to B together with the evaluation function. What does the evaluation function do? Well, it takes a function f and an argument a, and it returns f of a. This structure really has that universal mapping property, and it's uniquely characterized up to isomorphism by that universal mapping property. So if you like, you can take this as a definition of the set of all functions from A to B. In posets, too,
Can you explain how the diagram applies to sets?
Sure. Let's do that. That's a good idea. Okay, so here's the structure that I'm proposing to be the exponential. Yeah? And let's check that this really has that universal mapping property. So we'll check. So I'm claiming, my claim is that this is an exponential. My claim is this set together with this function is an exponential. Exponential in sets. So I have to check the universal mapping property. So we'll just write it out in the exactly the same way that I wrote it over there. I put the evaluation function right here. And now let's suppose, so here's b to the a. And now let's suppose I have some function here, f, on the product of these two sets into b. So this is a function in two arguments, right? It's got an argument from x and an argument from a. So now what I need to do is I need to get f bar over here. So what should it be? Well, f bar I'll define to be, well, it takes an argument from x, and it's supposed to return now a function from a to b. Well, what should I take? Of course, I'll take the function from b to the a. Of course, I'll take the function f bar x, which at an argument a gives me f of xa. It's the lambda transpose, the currying of this function in two arguments gives me here this function in one argument, taking values in functions. Yep?
So over here when you define exponential, kind of like before when we were talking about like a product is being a triple. So here an exponential would be like a pair of these.
It's a pair of things. It's a
epsilon?
Yeah.
Okay.
It's an object equipped with a map of this shape.
Okay.
And it's the universal such a one.
It would be great if you could include those when you define things. Just
It did. Where is it? Right here, exponential. An exponential is this thing and that is this.
Right.
I don't get what's funny.
Just it would be easier to say to read if it also said an exponential is the pair of either the a and epsilon such that, and then the rest of the picture.
Okay.
So other people agree, or
That's what I said. What?
Actually, it's a problem that several people have had 2 times already before. So maybe it could be a bit more explicit about what you think for a word.
Good. So the precise definitions are in the notes, folks. Okay. I'm not going to dot all the I's and cross all the T's here. I'm explaining how the machine works. If I do that, we won't get anywhere. But yes, so the exponential is the whole structure, just like I said before for the product. It's the whole structure. Okay, so let's check that this thing works. I take the transpose of f, and I give this function here, which is one argument, returning values in the set of all functions. And now I put it right here. So this is the function which is f bar crossed with the identity on A. It takes an argument here to an argument here and an argument x here to this. And now I compose with evaluation. What happens if I say evaluate after f bar cross 1a applied to some argument? So let's take an argument down here. That's going to be a pair xa. What does it give us? Well, first of all, I evaluate, and now I apply this thing. So that's f bar of x, and then here I just get a, because that's the identity function on a, right? And now the evaluation of f bar x to a is f bar x of a, which I already said is f of x. It's the definition of f of x a. So that's exactly f. Yep. So the idea is that this universal property captures this idea of currying and evaluation, yeah? But it does it wholly in terms of products and composition and universality. So let's look at some other examples. In, yep. Okay. So in the category of posets, it's easy to see, just the way that I did for products, that we can also make exponentials by equipping the function, by restricting the function space and then equipping it with the right kind of structure. So let's just do that quickly. So in posets, let's take the exponential of two posets p and q. There I'll take all the functions from p into q, but not all of them simpliciter, rather all the ones that are monotone. And then I'll order them f less than or equal to g pointwise. Okay. For all x and p, f of x is less than or equal to g of x. So that gives me the ordering on the set of all functions. And then the rest of the operations I can simply restrict. I can say evaluation is just set theoretic evaluation. And if I have x cross p and any monotone map G, then I take the transpose to be the set theoretic transpose. G bar. I don't know why I'm writing G. Oh, I guess I've used the F there. Then I just take the set theoretic transpose, and now what you have to check is the following. You have to check that the set theoretic evaluation map is actually monotone. Because I've defined the ordering here, I'm given the ordering there, I've defined the ordering on the product already in terms of the orders here, and that, I've said, is the set theoretic evaluation. So that's a well-formed problem now to show that this really is monotone. And then, given a monotone map like this, I'm taking the set theoretic transpose, it's called here, the associated thing here, and you have to check that that one's monotone with respect to the ordering that I defined there. And once that happens, then you know that this commutes because these were set theoretic operations. And then you're done. Right? So that's a sketch of the proof that posets has exponentials. Yeah.
So why the name that all the elements of q to the p are monotone?
You don't need that, but we're trying to find a poset which will have this property. And now I happen to know that this does the trick. You could try something else. This is exactly like the question, why did you order the product in the way that you did? This is the ordering that satisfies this universal property. And once you check that it works, then you know that that's what it must be. It's determined uniquely because of one plus 5 specification. You could try other things, right? And then you'll struggle and you'll find it doesn't work. And eventually you'll either give up or you hit on this, and then you'll say, oh, that must be it then. Does it make sense?
What is where does the fact that the element of p to the p are monotone?
In this proof, why you need it in the proof? You go through the details of the proofs. It's a good exercise to check.
But the idea of why we put monotone here is the idea that the exponential object must look like a function in this category?
Yeah, sure, yeah. This is a special case of something much more general, namely for two categories, D to the C, we can make a functor category, yeah, and that will be an exponential in cat. And we'll do that next time, but not yet, because here I need to say what the maps are between functors. The objects will be functors, the maps will be natural transformations, and that's the subject of the discussion. And then we'll show that that is an exponential in cat. Here, this is a special case of that. These are exactly natural transformations between these functors. Okay, so that's exponential. How about, oh, there's a homework exercise that I want to mention. I don't know if you can do it or not, but you might be able to do it, so it's worth a try. What about groups? Could you make an exponential of two groups, h to the g? Maybe you would try to say it's all the homomorphisms from g into h. Homomorphism. And then you'd have to say what the evaluation is and so on. So you could think about that and try to make that work. And the homework exercise is to show that this doesn't work. And there's a trick. Doesn't work. And the observation that you need to see that it doesn't work is that in any. Oh wait, I need a little bit more information here. Let me hold that thought right there and go over here and finish up a definition, and then I'll come back to that. I wanted to find the notion of a Cartesian closed category, and I need one more little bit of data, and then we'll have it. And then I can go back and show you what I have in mind there for groups. So a category is Cartesian closed. Cartesian closed. If it has the following. Well, it has products for any pair of objects. It has exponentials for any pair of objects. Of course, what I mean here is together with the rest of the structure. And then it has what's called a terminal object, which is a particularly trivial universal mapping property. Terminal object. So what's a terminal object? A terminal object, by definition, is this. Say 1. So here's the definition. 1 is terminal if for any object A there exists a unique map. Here, I'll use my convention there. A unique map down to 1. So for all A, there's a unique map from A into 1. So that's a kind of degenerate universal mapping property, isn't it? It has the existence and uniqueness built in there. And of course, any two terminal objects are going to be isomorphic, just because it's a universal mapping property. And just to give you a sense of what's going on in sets, any singleton set, any one element set is terminal. Similarly, in posets, same thing. In a poset, what's a terminal object? Well, it's an object such that any other object is below it, so it's a top element. Top element in the poset. Initial object, by the way, is the dual here, so that's the bottom element. That's the empty set in the category of sets as an initial object. Okay, so Cartesian closed category, I want to have not only binary products, but I want to have a terminal object as well. And then I want exponentials. And now let me observe that the universal mapping property of the exponent implies the following. applies the following two-way rule. Anytime I have, where is it? It's over there. X cross A, a map from X cross A into B, then there's a corresponding map from X into B to the A, right? That's this transpose business. Given F, there's a transpose like that. However, anytime I have a map like this, I can cross it with 1A and compose with evaluation and get a map like that. Given any map like that, some G here, I cross it with 1A, compose with evaluation, and get a map over here. Yeah? The universal mapping property says exactly that this correspondence, this two-way rule, is an isomorphism. Everything like this comes uniquely from a thing like this by that recipe crossed with A and composed with evaluation. Make sense? So the assignment that goes from here to here is take, the assignment that goes up the other way. The assignment that goes from here to here is take F bar, cross it with 1A, and compose it with evaluation. Take evaluation, compose with F bar, cross with 1A. Right? The universal mapping property says, given any one of these, there's a unique one of those, such that when you apply this operation, you get this thing back out. That's exactly what it says. So it says exactly that this is a bijection. We have this kind of two-way rule. It's just like the rules that we had for the product over there. And maybe this is a good time to emphasize, I haven't forgotten this uncashed check over there. I need to finish that sentence, but maybe this is a good time to emphasize the following. So, look. These universal mapping properties are like rules of inference, schematic rules of inference. Right, for the product, it looked like this. It said, given any X into A and X into B, you get a map from X into A cross B. Right? So if this is the F and this is the G, then this is the paired up F pair G. And given anything here, you compose with the two projections and you get these two things. So that's a kind of two-way rule of inference. Right? For the co-product, so that was for the product. For the co-product, it looks like this. It says, given any A into X and any B into X, you get A plus B into X. That's the co-pairing of those two maps. And given this one, you precompose with the two injections, and that gives you these two. What is the one for the exponential? Exponential. It says, well, it's that. It's that right there. Given any X cross A into B, you get X into B to the A. And back. Okay? And the recipe for getting back and forth is just this one that I've written down. So another way of stating universal mapping properties is in terms of bijections between maps of different shapes. So it looks like, it's starting to look like rules of inference for a deductive calculus. And in fact, that's what, if I have time, I hope to make that more precise. Okay, so now, what if we look at the case where X is 1? What do we get? What are maps out of a terminal object? They're like constant elements or points of a thing. So consider the case of X equals 1. Then we have 1 cross A into B corresponds to 1 B to the A. Now, it's an easy exercise to show that when you have products in a terminal object, that this thing is isomorphic to A itself. So this is saying that maps from A to B correspond to points of the exponential, constant elements of the exponential. Yeah. So that's the observation that I want to use to finish the sentence over there. In any CCC, points of the exponential here correspond to maps from G into H. But now suppose that this thing is a group. Okay? One is the terminal group. It's the one element group. It only has a unit, a group unit. And every homomorphism takes the unit to the unit. So there's only one homomorphism like this. If this thing is a group, there's only one map like this. And therefore, there can only be one map like that. So in general, if you have two groups, there are going to be lots of maps here. And so that's a sketch of why the category of groups cannot be Cartesian closed. Okay? Because if it were Cartesian closed, you would only have one map here, and therefore you would only have one map here. However, there's a more general notion of a groupoid. Remember, a group was a category in which every arrow is an isomorphism, and you only have one object. Well, let's throw out that only one object business, and we look at a category in which every arrow is an isomorphism, full stop. That's the notion of a groupoid. And now you can show that there's no problem with assuming if this is a groupoid and this is a groupoid, then this thing is a groupoid, and in fact you do get then a Cartesian closed category. So that's a good exercise, but it's a more challenging exercise. It requires that you go through various steps and think about it. But it's good to think about it. And next time when we do functor categories, the special case of groupoids will be exactly the case where these things are each groupoids, and then you make the functor category, and you get the exponential in the category of groupoids. All right, so I have a few minutes left, and really the whole point of this lecture was to connect up now with the lambda calculus. So let's do that without further ado in order to show that we have examples of all of these structures in the lambda calculus too. So the first thing I want to do is look at an example of, okay, so we're done with that, right? I can use this board. So let's look at exponentials in a poset. What is an exponential? Exponential in a poset. P. So an exponential in a poset would be a thing like this. So let's keep writing x, y, z for the elements of P. I'm going to use A, B, C too. So what would an exponential be? It would be an object B to the A, and it would have to have the following property for any x. If x is less than or equal to B to the A, then x cross A is less than or equal to B. But the product we know is a meet. So does that look familiar? Let's see. We need to have a gadget here which has the property that it's greater than any x, which when met with A is less than or equal to B. Well, that's usually written as a kind of implication in a poset. Let's write it like that, A arrows B. So, so the idea is we have A arrows B is a new element of the poset, and it satisfies this condition. So, for example, in propositional calculus, say intuitionistic or classical, this really is the A arrows B is the implication. So let's just check that that's the case for an implication in the propositional calculus. We need some rules. So let's take a propositional calculus with some variables and formulas that we build up in the usual way from conjunctions and implications. And we can put a constant true in there too if we want to. And then we'll have the rules. We can give them in any form we like. But let's just, to be specific, let's take a natural deduction setup. So if we have A, and we have B, and we have B, then we can infer this. And if we have this, then we can infer this, respectively, this. And if we have A, and we have A arrows B, then we can infer B. And if we have a proof of B coming from a hypothesis A, then we can cancel the hypothesis, the assumption there, let's label it U, and we can get A arrows B without any assumptions. So that's a kind of abbreviated or typical natural deduction setup for that fragment of propositional logic. Since we have true in there, we might as well allow ourselves to infer true from anything or from nothing at all. And now we need to check. So first of all, let's see that we really have a category, because I want to say that this thing is a Cartesian closed category, but I haven't said what the category structure is. So let's make a category, and the arrows will be implications. That is, if there exists a proof, right? Right. So this is, there exists a proof. So that's what last time what I called P, B, but now I'm saying if there exists a P such that A proves B. So those will be my arrows in the category. Good? It's obvious, I think, that A has an identity arrow and that we have a composition. You can just put the proofs together to get implies A, C, and that this is a pre-ordered category, pre-order. That is, there's at most one arrow between any two things. Just by the way, I've defined the ordering here. So that's my category. The objects are formulas in propositional calculus. The arrows are the deducibility relation. It's a pre-ordered category. And now the rules for the conjunction obviously make conjunction a product. So this is a product. The top is a terminal object, and we just want to check that this is an exponential. So what do we have to check? We have to check that if x is less than a, or if x proves AB, then x A proves B, and conversely. So let's check. Let's suppose that, this is an easy exercise, we'll just do one direction. Suppose that x proves A, B, and now we want to get this. So take x A, and we want to get B out of it, right? So first of all, we'll get the x, and then we use our assumption to get A arrows B. And then we use this assumption again, A, and we get the A. And now we apply A and A arrows B to get B. So that's our rule of elimination there. And that's the direction from top to bottom, right? And similarly, the other case will follow equivalently. And now you might wonder, well, what's the evaluation here, right? Because I have the two-way rule, but I haven't shown you what the evaluation is for the exponential. So the evaluation of the exponential, it should satisfy A arrows B and A proves B. So we have to check that there is a proof like that. Well, it's easy, right? You take the two projections and then you apply the rule for functions to get the B out. So that shows us that this propositional calculus is Cartesian closed, and that the implication operation in propositional calculus really is an example of an exponential in a category, just like the function set in the category of sets is an exponential. It satisfies exactly the same rules. What if we take, instead of the provability relation, if we take the category of proofs that we talked about last time? So let's do that. So instead of the propositional calculus, we'll now annotate all of these proofs with proof terms in order to get the lambda calculus out of this. So in light of the short time, I'm not going to rewrite it. I'll just say, take here some proof terms, right? Say alpha, beta, and then we take a pair, alpha, beta. And here is a projection. So if this is a gamma, then we take pi 1, say, or first of gamma has this type, second of gamma has this type, right? So if this is alpha and this is beta, and this is beta applied to alpha, and this is a lambda abstraction here. So if this is gamma, and this is a variable u, then this is lambda u gamma. Yeah? So now we're doing something richer than just this category of provability. We're doing actually the category of types that I think I talked about last time, didn't I? So now instead of this, I say this, and now I have real different proofs from A to B. There can be lots of different arrows from A to B. So this is no longer the case. I say P is an arrow from A to B if P is a proof, if P is an actual proof of A to B. So I take A, and I take P here, and I have B. And there can be different ones, right? Q, and so on, and so on. But it still is a category. It has identity arrows. It has composition of arrows. And now I would like to check that this category of proofs, it's also called the category of types. So category of types. Thinking of these things now as types in the lambda calculus rather than as proofs in the propositional calculus by the Curry-Howard isomorphism, right? Doesn't matter whether I regard them as proofs in the propositional calculus